think we can get started. So just an announcement first. All of the grades are posted, so you should have seen your grades by now. The numbers that you see have had 8 points added. And for those of you who are online, we've gone through all of them and hand corrected all of the fill in the blanks. So that's done. It's going to be a few days probably before we turn the zip strips loose. I want to make sure everybody's taken the exams. There were some people who had concussions and were ill, and so that's going to take a little bit longer, but I think it should be in the next few days. And again, if things didn't go well in this exam, you will drop the low score, so don't panic just yet. And if things didn't go well, think about going to the tutorial sessions. Think about spending more time in office hours. Think about how you're approaching the material. So often what happens up to the first exam is you're using your old tricks you've learned for the last 14 years to study for the exam, and they just don't serve you very well for these sorts of exams. And so try to think about how you'll change your approach to the material, and go to the TAs, go to the tutorials. If need be, we can get you some private tutors. We'll get you through this course. So there are many tools, just use them. So what are we going to do today? Today we're going to start down the road of thinking about the electricity inside cells. Neurons and muscles are said to be excitable cells. They're electrically excitable cells. And we're going to begin to see here today how these cells are electrically excitable. Yes, in the back.
Can you bring your volume up a little bit?
Sure, let me see. I can't tell. Is that better? Okay. Oh, I hate that. Let me take it down one. See if you can still hear it without the echo. All right. Okay, so try again. So what we're going to do today is we're going to set up the membrane as a place where we can store charge. And we have to think about how we're going to store charge across this membrane. And basically what we're going to be talking about here is something known as the resting membrane potential. Now for our purposes in here, we're going to emphasize that the resting membrane potential is close to the equilibrium potential for potassium. We'll see on Wednesday that there's a bit of a discrepancy, but for our purposes today, we're going to focus on the idea of the membrane potential being the same as the resting membrane potential being the same as the equilibrium potential for potassium. So we have to spend some time here thinking about how we're going to set up this potassium equilibrium potential, how we're going to set up the potassium battery. The first character we're going to invoke here is we're going to invoke the membrane, of course, but across that membrane we're going to put potassium leak channels. The hallmark of the potassium leak channel is that it's always open. The potassium leak channel never closes. It is not gated, so it's unusual among these channels. So it's open all the time. It provides a pathway across the membrane for potassium to move. And the way we're going to set up this thought experiment is we're going to put 100 millimolar potassium on the inside of the cell and 10 millimolar potassium on the outside. We'll see a little later that those are not biological concentrations, but for our purposes today, they work pretty well because of the numbers. So we have 100 millimolar potassium on the inside, 10 millimolar potassium on the outside. Potassium starts to run down its concentration gradient. And if we only had the potassium leak channels, then the potassium would leave, and of course, all of the potassium would run out into the ocean. But there are another set of characters here which slows that process down by a whole lot. And that next set of characters are going to be the large negative anions. These are the large impermeate anions. So they're negatively charged. So under these circumstances, potassium starts to run down its concentration gradient, but it doesn't take very many to leave before the large negative anions now affect their strength on the positively charged potassium ions and hold them in place. So at that point, we've reached an equilibrium where the tendency of the potassium to run down the concentration gradient is balanced by the tendency of the charge and the large negative anions to hold those channels, to hold those charges in place. We've reached a kind of equilibrium. That equilibrium is stable, but it doesn't give us very much insight into how biology uses this battery to signal. And that will be the next step. How do we change that equilibrium? How do we upset that equilibrium? The way we're going to upset the equilibrium is with a new set of channels. These will be what they call voltage-gated channels. These are going to be the gated sodium channels. So we're going to set it up first with just potassium. Then we're going to imagine a situation where there's 100 millimolar sodium on the outside, 10 millimolar sodium on the inside. Now, if there are no gates, it doesn't matter. I'm sorry, if there are no sodium channels, it doesn't matter. But now if we put sodium channels across the membrane, if we just have them open, then we have balance in the sodium and potassium. But sodium can't come through. Magically. Open and imagine what's going to happen. The other caveat we're going to place on this is that there's probably an order of magnitude, maybe 2 orders of magnitude, maybe 3 orders of magnitude more sodium channels than potassium leak channels. That brings us to an important concept. It's a mantra. I'll ask you to know this mantra. It'll help you think about this a lot. And the mantra says that the membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. So what we're going to do is we're going to first set up an equilibrium potential for potassium. We're going to say that the predominant permeability is to potassium, so that means the resting membrane potential is going to be around potassium equilibrium potential. Then we're going to change the story, leave everything in place, but now we're going to add the sodium channels. Open the sodium channels. Now the dominant permeability is to sodium. So the mantra says the membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. The dominant permeability is to sodium. We're headed to the equilibrium potential for sodium. Then we're going to talk a little bit about how we can regulate the openings of these channels. And we can regulate the opening of the voltage gate of the sodium channels by something called charge. In other words, they're voltage gated. When we say a voltage gated channel, we just mean a charge sensitive channel. The channel is sensitive to charge. When it recognizes positive charge, the gate swings open and sodium comes in. And we'll walk our way through that and talk a little bit about work. The other characteristic of these sodium channels is that they're said to have a threshold. And if you put your phone away, I'd appreciate it. The sodium channels now have a threshold so that they start to open with sodium, but then the more sodium comes in carrying positive charge, that positive charge now tells the neighboring sodium channels to open. As long as we're just opening 1s and 2s, it doesn't much matter. The dominant permeability will remain potassium. But as soon as we start to open groups of these sodium channels, now the dominant permeability is to sodium, and we're headed toward the sodium equilibrium potential. And we'll walk our way through that. But one of the characteristics of these voltage-gated sodium channels is up here. They inactivate. Now we're going to talk about something called the ball and chain. The ball and chain is a piece of the cytoplasmic region of this voltage-gated sodium channel which swings into place and blocks the channel. That's called inactivation. These channels, the voltage-gated sodium channels, remain open only briefly, only about a millisecond or maybe 2. Then the ball and chain moves in, closes off the channel. At that point, the dominant permeability will be to potassium. But we have a limited amount of potassium permeability because we only have a handful of those leak channels. So biology, in order to maintain speed, in order to increase the rate at which we can repolarize the membrane, introduces a new kind of voltage-gated channel, the voltage-gated potassium channel. So now we start to open the voltage-gated potassium channels, the dominant permeability to potassium. We drive the membrane potential back toward the equilibrium potential for potassium. So we have a kind of switch. We open the voltage-gated sodium channels, depolarize the membrane to plus 40 millivolts, turn those channels off, open the voltage-gated potassium channels, and repolarize the membrane. Now, one of the major differences between the voltage-gated sodium and voltage-gated potassium channels is that the voltage-gated potassium channels are slow to open. That gives them a name. They're called the delayed rectifiers. It's a great name because it tells you they're delayed in time and they rectify the membrane potential. So we'll work our way through all of that, and if there's time, we'll get into action potential propagation, but I suspect that's going to be Wednesday. But let's start out here talking about how we can generation of the resting membrane potential, which for today's talk is going to be the potassium equilibrium potential. Potassium equilibrium potential said to be EK. Let's think about that. I'm going to draw two parallel lines. We can imagine this is a proper cylinder. On the outside, I'm going to put millimolar potassium. And on the inside, I'm going to put 100 millimolar potassium. Now, in biology, these numbers aren't quite the same. I'm doing this because it's a thought experiment. In biology, these are going to be more like 104 or 5, but this will work for our purposes. Then, across the membrane, I'm going to put just a small number of these so-called potassium leak channels. Remember, the potassium leak channels are always open. They're never gated. They're always open. Now, if we just set this up this way, and we imagine out here is ocean, imagine here's inside the cell, you can see what's going to happen. It won't be very long before this potassium runs down. But biology has a way of slowing that down by orders of magnitude. And what it does is on the inside of the cell, it adds these large negatively charged anions, which we denote as A negative. These are said to be large, impermeant anions. The name tells you a lot. They're impermeant. They can't move. They're too big to go across the membrane, and there are no channels for them. So they're stuck on the inside. They're from a variety of molecules, probably some proteins, but the long and the short of it is they're big and stuck inside the cell. Now imagine potassium starts to go down its concentration gradient, runs out through those potassium leak channels. It doesn't take very many potassium ions to move down the concentration gradient before these large impermeant anions, the charge on the A negative prevents potassium movement down its gradient. So these guys are positively, they're opposite charge, negative charge on the anion, positive charge on the potassium. So potassium starts to run down its concentration gradient, but then the charge on the negative, the opposite charge on the anion, holds in place. So it can't move. That reaches a kind of equilibrium. So we can say that we've reached an equilibrium between the probability of ion movement, I should say potassium movement down its concentration gradient. And the electrical gradient. Produced by the A negative, the large impermeant ions. So we've reached an equilibrium. Now, if you understand this concept of how it gets done, that's all I ask. But I'm now going to walk you through just a short equation. And I think if you spend some time with this equation and understand what the equation means, what it's telling you, that you'll understand this whole concept a lot better. And the equation is said to be the Nernst equation. It's named after an early 20th century physical chemist. He worked in Berlin. If you put your phone away, I'd appreciate it. I would appreciate if you put your phone away. Thank you. So he was an early 20th century physical chemist. And he worked with Boltzmann. So Boltzmann is a very famous late 19th century physicist. And he used the Boltzmann equations. Boltzmann worked out all these different equations. And he modified the Boltzmann equations for biology. And this is the Nernst equation. And it says that the equilibrium potential for potassium is equal to RT over ZF. Now, this looks like a lot. If you take a moment, it's not so bad. R is just the gas constant. T is temperature in degrees Kelvin. F is the Faraday. It's just a means of converting numbers of charges to molar concentration. We're not going to worry about any of that. That's going to become... It's RT over ZF times the natural log, ln, of the potassium concentration on the outside divided by the potassium concentration on the inside. In one fell swoop, we're going to change this number and the natural log into 58. Turns out, if at room temperature, you use the room temperature and then you use the calculations, the rest of it, and you convert natural log to log base 10, this comes out to be 58. 58 times the log base 10, the potassium concentration on the outside, divided by the potassium concentration on the inside. Well, in our thought experiment, we've set this up to be 10 and 100. And so that means we can say 58, so that the EK is equal to 58 times the log base 10 of 10 divided by 100. Get rid of this. And if you do that, then EK is equal to 58 times 10 divided by 100. This is 10 divided by 100 is 0.1. The log of 0.1 is minus 1. It's just simple math. So now we have EK is equal to 58 times minus 1. So it's minus 58 millivolts. That's the equilibrium potential for potassium. Now, these numbers will change a little bit. If you plug in the numbers for biology, you've got to use potassium on the outside about 4, potassium on the inside about 110, and you have to change the temperature from, 20 degrees centigrade to up around 37. And if you do that, you come out with a number for biology of about minus 70 to minus 80 millivolts for EK. But all I'm trying to do is show you how we can use the ratio of the potassium ion concentrations to determine the resting membrane potential. If you spend a little time staring at this equation, you'll also recognize, because of this log arrangement, this log base 10 arrangement, it doesn't take much in the way of a movement, a change in the extracellular concentration, and you're going to shift the membrane potential a whole lot. And that's important biologically. So now we've said that we have enough charge on the inside, and it's going to be mostly negative, so that we're at minus 58 millivolts. And this minus 58 millivolts is EK. So we've set up the membrane potential. We've set up the membrane potential based on the potassium battery. And the potassium battery and the Nernst equation is telling us that the membrane potential in here is going to be minus 58 millivolts. But now we're going to change the zoo of ions that we have here. And out here, we're going to put 100 millimolar sodium ions. And on the inside, we're going to put 10 millimolar sodium ions. With no pathways, it doesn't make any difference. But now, let's put some channels across the membrane. And I'm going to label these as sodium channels. These are sodium selective channels. So under these circumstances, the sodium will come rushing down its concentration gradient and come in. But we put a caveat. There's a limit on these sodium channels, and that is there's a bar across the channel. This is said to be the gate. This is telling us that the sodium channels are gated. So now we still have 10 times as much sodium in the outside as in the inside. The sodium's trying to run down its concentration gradient, but it can't. It can't because these gates are closed. So we're at equilibrium. We've reached the equilibrium potential for potassium by having the potassium leave and come in balance with the large negative anions. And then we've put in these sodium channels, but nothing changes as long as these gates are closed. But now let's imagine that we have not just 3 of these sodium channels, but let's say we have 3,000 of them. And let's say that suddenly, magically, we'll see in a little bit, we can do it by charge, but suddenly we open all of these sodium channels. So now we have this massive number of sodium channels open. So we can say that we have increased the membrane permeability that's an L to sodium. So under these circumstances now, the dominant permeability will be to sodium, and sodium's going to come rushing in. Well, we can set up the same thing over here. We can do the same thing for sodium. We can say the equilibrium potential for sodium, because we're going to see each ion has its own equilibrium potential. Biology will work through this for all these different kinds of ions, each one with a separate channel. But for now, we can say the equilibrium potential for sodium is equal to, again, RT over ZF times the natural log of the sodium concentration on the outside divided by the sodium concentration on the inside. Again, this, by changing from natural log to log base 10 and the RT over ZF, that comes out to be 58 at room temperature. So now the equilibrium potential for sodium is equal to 58 times the log of 100 divided by 10. Well, this comes out to be 58 times the log of 10. 100 divided by 10 is 10. So this means that log of 10 is equal to 1. So that means it's 58 times 1, which means we have plus 58 millivolts for the equilibrium potential for sodium. So we set up the potassium battery, we put in the sodium channels, and we suddenly open the sodium channels. Now I'm going to put on the board a mantra. And this mantra, I think, will help you understand a lot of what's going to be going on here in the next couple of days. And the mantra says that the membrane potential seeks the equilibrium potential whose permeability is dominant. It's a very famous equation that covers this. It's called the Goldman-Hodgkin-Katz equation. And if you take a neurobiology course, a cellular biology course, you'll go through all of that. But the long and the short of it, it says the same thing. The membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. Using that mantra, we start out where we only have the potassium leak channels. Well, let's go ahead and put the gates on these first. So we start out where the only permeability across the membrane is potassium. The membrane potential seeks the equilibrium potential for the ion's permeability. That's potassium. We're headed toward EK. But now let's imagine that we suddenly open all of these sodium channels. Not just 3 of them, not 3 versus 2. Let's say there's 3,000 versus 2. So what's the dominant permeability for the membrane? If we open all those sodium channels, what's the dominant permeability? Be sodium. The membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. That means we're headed to EK. So we can graph this. We can show this on a graph. And if we do that, on the axis we have time. On the ordinate, it's voltage. We're going to start out here at minus 58 millivolts. This is our thought experiment. And the membrane potential is stable. We're at equilibrium. We're at EK. But then at this point, we open all available sodium channels. Now there's a caveat here, all available. I'll tell you why that's a caveat in a moment. But we now open all the sodium channels, so now the membrane potential goes from minus 58 to plus 58. So we have depolarized the membrane. We've depolarized it from minus 58 to plus 58 simply by opening the sodium channels. Now, as long as the sodium channels are open, the dominant permeability is to sodium, then we're up here. That's not a very good signaling mechanism, just to switch the membrane polarity from minus 58 to plus 58. To be a proper signaling mechanism, we now have to change this membrane potential back to where we started. So the first thing we do up here is we turn off the sodium channels. In biology, doing this is said to be sodium channel inactivation. Typically, we show this diagrammatically. It's not accurate biologically. We know what the amino acid sequences are, but we can think of it this way. This is meant to be the channel. There's meant to be a gate in here. And then down here on the cytoplasmic side is something I'm going to label as the ball and chain. It's not exactly descriptive. It isn't really a ball and chain. It's really a fairly short segment of amino acids. But for our purposes, it works pretty well. You can imagine that there is this region of the membrane on the cytoplasmic side. So let's put the membrane in here. So this is out, this is in. The sodium has come through the channels. And at that point, after the sodium has come through the channels, this ball and chain moves up into the channel and blocks the channel. This appears to be a stochastic event, just simply happens by time, but it's fast. The ball and chain will move into the mouth of the channel in about a millisecond, at most 2. And so that means that we open all the sodium channels at one time, we depolarize the membrane potential to plus 58 millivolts, but then we inactivate those channels. Well, up to now, if we've inactivated the channel, so we've moved the ball and chain into the channel, and everybody's closed, and the only channels we have left open are the potassium leak channels, we can again use the mantra. Membrane potential seeks the equilibrium potential for the ion's permeability is dominant. the dominant permeability is potassium, so now this membrane potential is going to come back down, but it's going to be slow. If we only use the potassium leak channels, this so-called repolarization be in terms of seconds to minutes, and we need something to signal in terms of milliseconds. Yes?
Is the ball and chain voltage activated?
So the question is, is the ball and chain voltage activated? No. The ball and chain is only activated by time. And the way I imagine it is it's sitting down there in the cytoplasm flopping about. And it doesn't matter if the gate's closed, it can move up, it doesn't make any difference. But once the gate's open and it's flopping time by random movement, it will swing up into the channel. So it's entirely stochastic and time dependent. Yes?
So as soon as that sodium channel opens and we get polarization, do we immediately close it and go back down? Or is there like a plateau at the top?
It's a great question, and that's what I want to address here. The way I've shown it is that we could have a long plateau depending on how long it takes to inactivate them, but it's pretty fast. But the way I've shown it is we have the membrane potential coming back down pretty slowly because we only have potassium leak channels. But now what I'm going to do is I'm going to change the story. I'm going to add a new set of channels. Now I'm going to add a set of channels that are potassium channels that are charge activated. Okay? And then we'll come around and talk about these two kinds of charge activated channels. So the other character up here across this membrane these are the voltage-gated potassium channels. Again, they're charge sensitive. Say, in fact, I should come back to this, that these sodium channels are the voltage-gated sodium channels. So when we say they're voltage gated, what we mean is that there's a region of the cytoplasmic side of the membrane that's charge sensitive. We know what that is. What happens is that when we get positive charge on the inside of the membrane, that positive charge forces four of the transmembrane regions here. There are 24 of them. And there's one region called S4. It's a repeat of, there are 4 S4s. Those S4s are an alpha helix. Let's see if I can draw it in backboard. The S4 is an alpha helix, and it's interacting with other alpha helices. And if we put the membrane here, if this is S4, once there's positive charge on the inside of the membrane, that tells the amino acids on this group that we're interacting with amino acids on neighboring alpha helices because they were oppositely charged. Now tells this alpha helix to move. It pops up out of the membrane. When it pops up out of the membrane, we now know that this is linked mechanically. It's amazing to me it's mechanical. It's linked mechanically to the gate. And when the S4 moves, when 4 of these S4 regions move, they pull on the gate and they literally open the gate. When they open the gate, the ions come in. Then the ball and chain moves in and we close the channel. That's how the voltage-gated sodium channels work. The voltage-gated potassium channels work in a similar way. The voltage-gated potassium channels, too, are charge sensitive. They, too, have an S4 region on them. When they recognize the increase in positive charge, which has been delivered by the increased sodium, they then open. So let's look what happens up here. Sodium channels have opened. They've recognized positive charge. They depolarize the membrane to plus 58 millivolts. But then the ball and chain moves in and they inactivate. At this point up here, at this point, the voltage gated potassium channels open. So where before we had a limited permeability to potassium, now with the voltage gated potassium channels opening, we have a dominant permeability to potassium, and we can rapidly repolarize the membrane back down to rest. So there's a lot in that. So let's walk through it one more time. We start out with the potassium battery. The potassium battery is generated by only the potassium leak channels. Potassium leak channels provide this membrane potential because as the potassium leaves, it comes to equilibrium with a large negative anions. And it's a stable state. We're at minus 58 millivolts. Then in some way, there's an addition of positive charge. The positive charge opens the sodium channels. It turns out that the opening of this sodium channel will lead to the opening of this sodium channel, which will lead to the opening of this sodium channel. But for our purposes right now, we've suddenly opened all the sodium channels. The number of open sodium channels is several orders of magnitude greater than the number of potassium channels. So we had a limited potassium permeability with the leak channels. Now we have a whopping sodium permeability with the open sodium channels. The mantra says that the membrane potential is going to go toward the sodium equilibrium potential because that's now by far the dominant permeability. So the membrane potential now goes up to plus 58 millivolts. The sodium channels only remain open briefly though. Ball and chain moves in, and then the potassium channels start to open. They too open because of an increase in the amount of charge. But the major difference between the potassium channel and the sodium channel, in addition to the ion it's carrying, is that the potassium channels are slow. In fact, they're said to be the delayed rectifier. They're delayed time. So I think of them as being kind of lumbering, where the sodium channels are really quick. They swing open and depolarize the membrane. Then after the sodium channels have begun to inactivate, along comes the lumbering potassium channel. Potassium channel opens, and now the voltage has caused a massive increase in the permeability of potassium, and the membrane potential now goes back down to the equilibrium potential of potassium. Again, the dominant permeability is to potassium. So we have a kind of switch between sodium and potassium, sodium, potassium. And each time we do that, we can change the membrane potential to plus 58 and back down again. Now, one of the, yes?
So we just have these voltage-gated potassium channels just to rapidly depolarize as opposed to kind of like slowly depolarizing?
So the question here is, what's the purpose of the voltage-gated potassium channels? Why can't we just get by with the potassium leak channels? After all, that's the dominant permeability. The answer to that is that there are so few potassium leak channels that it takes seconds to drive the membrane potential back down to rest again using only the leak. But if we open those voltage-gated potassium channels, we can return the membrane potential back down to rest in a fraction of a millisecond. So it's all about speed. And then we can fire another action potential in a matter of another 10 milliseconds or so. Really fast cells will fire as many as 100 action potentials per second. It's unusually fast, but they can do that. So we need speed, and the way we get the speed is we get rapid depolarization and rapid repolarization, and start all over again. Anything else? Yes?
And it seems like require any somewhat like active transport. It's all like just happening.
Okay, so now is the question that always comes up. So you're telling me that this goes on forever. It's a perpetual motion machine. And I'm telling you no. But what I do want you to recognize is that we can do all of this with just ion channels. So let me walk through it. One of the things that certainly was confounding to me when I first learned this is that you have two positively charged opposite things. Sodium comes in, depolarizes the membrane, and then the only way we return the membrane potential back down to a negative potential is to get potassium to leave. How do you manage to do that using 2 positively charged ions. So let's walk through it, and then I'll answer your question specifically. The answer to that is that if we look at the concentration on the inside of the cell, so that we start out with 100 millimolar potassium and 10 millimolar sodium. And we open the sodium channels, and sodium comes in. This action potential, the depolarization all the way up to 58, and the repolarization back down to 58, the concentration change that results from that will take the sodium concentration from 10 millimolar to 10.0001 millimolar. Not many ions move. It's a fundamental idea here, and it's hard to get your head around. But the concentration changes are tiny. So now we've had an action potential. And also on this side, we've had potassium leave. So at the end of the action potential, the concentration of potassium has gone from 100 millimolar to 99.9999 millimolar. So we get these vast changes in charge with small changes in concentration. This brings us back to your question. What this tells us first is that we can have many, many action potentials without changing the concentration much. Roughly 1,000 of them in a big axon. So, but it's not a perpetual motion machine because you're right. Sodium is coming in, potassium is going out. And eventually we have to invoke the pump. Eventually we have to invoke the sodium-potassium pump. To bring the concentrations back to normal. But we don't need to activate the pump simply to change the potentials across the membrane. We can do that simply by opening the channels. And one of the confusing things here is that it's potassium that's leaving the cell. It's potassium leaving the cell that's driving the membrane potential back down again. And yet potassium is a positively charged ion. But if you look carefully at those concentrations, it's the only charge carrier you have that can exploit those concentrations. So the potassium now moves down its concentration gradient and removes positive charge. Very many positive charges to change the membrane potential. You don't have to change the concentration. You just change the number of charges. Now you're right, over time, over thousands of action potentials, you have to invoke a pump. But we can poison that pump and get hundreds, in a large axon, hundreds to a few thousand action potentials before that gradient breaks down. Does that answer your question? Okay. Yes?
Are those channels only on the top layer of the membrane, or are they on both?
So where do we put the channels? I just put them on top because it's convenient.
Okay.
But in fact, they're all over.
Okay.
We'll see a little later when we talk about myelinated axons. They're going to be clustered at the nodes of Rambouillet. But for now, they're all over.
Thank you.
Anything else? Okay, so a couple of other points I need to talk about. Let's go to the backboard. This is the concept of threshold. Threshold has a definition. Threshold is defined as the potential. I should say membrane potential. The membrane potential at which sodium influx, we can say through voltage-gated sodium channels, is balanced by potassium efflux through potassium leak channels. I imagine this is standing on a knife edge. So you're right balanced on that knife edge so that sodium coming in and potassium going out exactly equal to the knife edge. If you push just a little bit more sodium in, then you have more sodium coming in than going out. At that point, all sodium channels in the neighborhood are going to open simultaneously and drive the membrane potential toward the equilibrium potential for sodium. See if we can think about this in a kind of graph. I'll use our numbers of -58. And that's the equilibrium potential for potassium. Again, I'll remind you in biology, this would be more like -70, -80. And then we can imagine here that sodium channels flicker open. We theorized above that all those sodium channels are going to open simultaneously. But now we're going to imagine that they're opening in 1s and 2s. We can say that they're opening in these little bumps. So each one of these little bumps is meant to represent a sodium channel opening. And then there's a point up here, and I'm going to give it a number. It's variable in different cells. It may be quite a wide range. We're going to say it's -55 millivolts. And we're going to give this voltage a name. It's called threshold. So from the definition, if we're right at threshold, we're on this knife edge here, where sodium influx through the opening and the flickering of these sodium channels is precisely balanced by the efflux potassium through those potassium channels. And it could stay there for a long time. But then something happens, and we slightly increase the number of open sodium channels. When we opened a few more sodium channels, suddenly we're beyond the knife edge. Now sodium is coming in. Remember what that sodium charge is. Sodium charge is positive. So that means when the sodium comes in, through these channels, it's carrying positive charge. As long as these are small numbers of sodium channels, the potassium the open potassium leak channels can compensate for them. But if suddenly we now get a surfeit, a whole bunch extra sodium channels opening so that the sodium in here exceeds threshold, the number of positive charges exceed threshold, then all those sodium channels in the neighborhood open all at one time. So that when we look at this graph here, at threshold, we slightly increase the number of open sodium channels. All sodium channels nearby open simultaneously. If all the sodium channels are opening simultaneously, what does that tell you about the permeability to sodium? Well, it's going to be a whopping sodium permeability, and so now the membrane potential goes up to +58 millivolts. But those channels remain only open briefly. So at this point, we have sodium channel inactivation. And as those sodium channels are inactivating, the delayed rectifiers, the voltage-gated potassium channels now are turning on, driving the membrane potential back down to rest. And this is meant to be the voltage-gated potassium channel opening. Of course, when we talk about permeability, this is increasing the permeability to potassium. The dominant permeability is potassium. The membrane potential is being driven back down to the equilibrium potential for potassium. At this point, we can start all over again. And we can do that hundreds of times without invoking the pump. over and over again, repeating this cycle. And that's because this entire cycle requires a fairly large neuron, no more than a few million charges, hardly changing the concentration at all. So any questions on that before we go? Yes?
At the end of the wave where it goes under.
Aha, okay. You're asking something that normally you've seen in another place, where it does this. It's called the undershoot. I'll let you think about that. And I'll let you think about that till next time. Remember, we have high potassium permeability here. Sodium channels have been inactivated. What must be going on out here at rest with the sodium channels? They're flickering open and closed.